Okay, here we are back with more homework helps. You see on the screen an example of my daughter's very unusual artistic sensibilities, so I better clear that before you get too good of a look. Okay, I'm doing 8.1 A and C. So here we have an interface, and on this side is air. So it's convenient to change the notation a little bit. Instead of calling the regions 1 and 2, we'll label them 0 as 1, 0 and 1. So that way we have eta naught on this side for the characteristic impedance. And in the dielectric material, we'll call that eta 1. And in eta 1 will be the epsilon r equals 25 down in the denominator. So this will be square root of mu naught over epsilon r epsilon naught. So there we have our two materials, the air and the dielectric. Now the power going to the right is this way, and that will be E naught incident magnitude squared over 2 eta naught. The reflected power is the same thing, but with a reflection coefficient inserted. So that product together is the E naught reflected over 2 eta naught. I forgot the naught down there. The power going to the right is the transmitted power, and that's tau, the transmission coefficient, E naught incident magnitude squared over 2 eta 1. And of course, here we have to be careful to use the right characteristic impedance for the medium to the right, not the air. Okay, so that's 8.1 A and C, and you can use those formulas to guide you a little bit as you do part C. Now we'll go to 8.3A. So here we've changed the orientation of the picture a little bit, so we have to think about how to draw the picture. The interface will be this way, and this will be the z direction. Y is to the right, because if you look at the expression for the incident field, it's propagating in the y direction. And if you do a little bit of right-hand rule, x is coming out of the board. So there's our coordinate system. And this is epsilon r1. 9 is given in the homework problem, and epsilon r2. Now that sets up the problem. So the incident wave is propagating in the plus y direction. We can see that from the cosine omega t minus ky in the given incident field. The reflected wave will have a cosine omega t plus ky, and we need to make sure we use the correct k value. That's the k with epsilon r1 in it. And the transmitted wave will be cosine omega t minus k2y, and that k2 will have the epsilon r2 in it. And then I'll let you plug in the different amplitudes. The incident field has a 2 in it. This would have a 2 and a gamma. And then for the reflected field, the transmitted field will have a tau in it. And then you'll have to add in the z hats for all three fields. So amplitudes and vectors everywhere, and then that'll complete that problem. Now I'll move on to 8.16. The key to that problem is to know that the electric field is E of z is equal to, now let's draw a little picture. So here we have the ocean surface. We have an incident wave. There's some reflection from the ocean surface, but what we care about is the transmitted field. So once we get inside the surface, we'll have the incident field amplitude that's given in the problem. That's the 3,000 volts per meter. Then we'll have a tau, a transmission coefficient, and we'll have an e to the minus alpha d. And we have to put that all in magnitudes. There's also a phase term with the beta from the lossy medium treatment. This expression shows how the field starts at tau E naught incident and then decays. So right here, right when we get across the seawater, we have tau E naught incident. And once we start propagating into the water, then we pick up the e to the minus alpha d term. So you have a value for this. You can compute the transmission coefficient. You get alpha from the lossy materials formula. That's the square root of minus omega squared mu, and then epsilon minus j sigma over omega, going back to lossy medium materials. And given a value for E of z, you can go back and back out the d that will give us that value. So there's helps for 8.16. Now we'll move on to 8.9. For that problem, we want to use a transmission line analogy. So for wave propagation, we have three materials with an epsilon 1, epsilon 2, and epsilon 3. And the math is identical to a system of three transmission lines with a Z1, Z2, and Z3. And to complete the analogy, we would compute the Z's as eta values with the three epsilons in them. And the key to this problem is that we're going to use a quarter wavelength section for region 2. And then looking in, the Zn will be Z2 squared over Z3. And we can solve that for Z2. And in turn, we can solve that for epsilon 2. And then we have the solution to the problem. So you're going to give a formula for lambda 2 over 4 and for epsilon 2, and that is that problem.